let's continue. We were doing the conductors in series and parallel. So far we did the series one. So we said if there's a wall, and we have here T1, T2, you have two conductors, K1, K2, and then this is delta X1, delta X2. So remember the argument we made is that the power that goes through one is the same as the power that goes through the other one. So P1 equals P2, which equals P total. And then what adds up is the temperature difference, which is similar to saying voltage adds up in series. So delta T1 plus delta T2 is equal to delta T total. And then you use the equation P is Ka delta T over delta X. So you solve for delta T, P delta X over Ka. Then you substitute P1 delta X1 over K1 A1 plus P2 delta X2 over K2 A2, P total delta X total over K total delta A total. Okay, and then you say, well, whatever is the same we can cancel. So we're going to say the same power goes through here as through here. So then that one we cancel, and whatever else, the area, the surface area, this cross-sectional surface area is the same. So that one also cancels, and we get here, and then instead of delta X, we'll just write as H1, H2. So H1 over K1 plus H2 over K2 is H total over K total. And then we did an example of that for a house that had 3 layers. The wall had 3 layers, 2 dry walls and a fiberglass. And then we added, so if you have 3 in series, you can just add easily like that. So remember that this one, the top one could be in centimeters or meters because the units of that cancels. And then the units of the K total comes out the same as the units of the K1, K2, okay? Now we're also gonna define something else. This is just a definition called insulation factor, or insulation factor. And the definition of that, when I do 3 lines like this, it means that's basically how it's defined. So then the definition of that is going to be H over K. So in other words, something that has low conductivity and it's also thick, it's going to be the best insulator. If the conductivity is low and it's also thick. So the insulation factor is going to be the best. So it's kind of like what we do in electricity when we have resistivity is 1 over conductivity of a material. So if it's electrically bad conductor, then it's a good resistor. Except now we're applying that to the total resistivity. So it also depends on the thickness. So not only the material, if it's a poor thermal conductor and also thick, then it's going to have a good resistivity, thermal resistivity. So then obviously the opposite will be true. If it's a good thermal conductor and very thin, the opposite will be true. The insulation will be low, right? So the units of the insulation factor will be meters over the units of the conductivity, which was what? Remember the units of K were, so if you always forget, you can go back to the equation. You can say this is watts, this is meters squared, this is Celsius over meter. So, and then the units of the K, one of the meters cancels. So K must be watts per meter Celsius. Or you have different versions. You can say calories per second meter or centimeter Celsius. So as long as you got, because remember watts is a joule per second, so you have units of energy per time, per thickness, per Celsius. And then the other one is British thermal units per hour, per foot, per Fahrenheit. So that would be the units of the K. So now the units of the insulation factor would be opposite of the K, plus you got the thickness of the material. So then you got here, so meters divided by watts per meter Celsius. So then it's gonna be meter squared Celsius over watts. Then of course you can have all the other versions too. So you can have centimeter squared Celsius over calories. So, I'm taking this one and then reciprocating that. So, no, it's gonna be centimeter squared seconds times Celsius, right, over calories, that's it. So take this, reciprocate it, and add a thickness, another extra unit of thickness to it. So feet squared over times hour times Fahrenheit over British thermal units. So if we look at some insulation factors, see here, the insulation factor, Fahrenheit, feet squared, you see where that is, hour over BTU, meter squared, Kelvin over watts. So R value units, as we said before, the R value measures the thermal resistance of a material, you see, whereas the K is the thermal conductivity. So this can also be expressed as a temperature difference that will cause, the temperature difference that will cause 1 unit of heat to pass through 1 unit of area over a period of time. So in other words, how much temperature difference does it take to cause 1 unit of British thermal unit to transfer through 1 foot squared of area for every 1 hour? That's kind of the way to look at it. You see? So if it takes more temperature difference, right, for 1 British thermal unit to transfer, then the R value is more. So that means it's better insulator. You see? So the bigger the R, the better the insulator, the poorer the conductor. Opposite. You see? That's the idea. So in the equation below, the imperial units are shown on the left and the SI units are shown on the right. So it says R values are additive. For instance, if you have a material with an R value of 12 attached to another material with an R value of 3, then both materials combined have an R value of 15. So I guess one of the reasons why we do the R value is because we can now write this as what? H1 over K1, we can write it as R1 plus R2 is equal to what? R total, right? So it makes it easier. We can say, if you have 1 insulator with 12, attach another one with 3, you get 15. Kind of like electrical resistors in series, right? If you have a battery, and then you have one electrical resistor, another electrical resistor, 10 ohms, 20 ohms, and then the combined resistance is 30 ohms, right? So when you have two electrical resistors, they become bigger resistors because the electricity has to go through two wires now, so they resist the flow of electricity more than they would each individually. Well, two heat resistors in series will also add up, just like two electrical resistors, you see. So it's kind of a good way to remember them, the fact that they're additive like that. And that's what they mean here. 12 and 3 gives you 15. What are U factors? What is that? Many energy modeling programs and code calculations require a U factor, sometimes called U values. The U factor is the heat transfer coefficient, which simply means that it is a measure of an assembly's capacity to transfer thermal energy across its thickness. The U factor of an assembly is the reciprocal of the total R value of the assembly. The equation is shown below. So then they now reciprocate that, right? So you combine all the R's, then you reciprocate. So if it's a big resistance, then the U factor is low, right? So you can keep doing this and defining new concepts. So in some cases you want the R factor to be low, the U factor to be big, and then the R factor to be big or the U factor to be low. So it depends what your goal is. A lot of websites will give you the R value in the American system, Fahrenheit square feet hour. Especially like building materials. Exterior, 0.17, interior wall, airspace, so gypsum wall board. So of course it depends on the thickness, you see, the R value. So it's saying a gypsum wall board 1/2 inch, 0.45. Gypsum wall board 5/8 inch, right? So what should happen? Is it linearly proportional to thickness? So if it's 5/8, this one should be bigger than this by the ratio of 5/8 to 1/2, right? It should be linear. Why? Because our insulation factor is linearly proportional to the thickness. You see? So if you have the same material, if I make it twice as thick, R should go up by 2. If I make it 3 times as thick, R should go up by 3. So if you look at a table like this should be, you see, like plywood, 1 inch, should be twice as much as the 1/2 inch. Yeah, pretty much, you see that? And then it keeps going like that. Fiber board sheeting, medium density particle board. So of course, the bigger these numbers, the better insulator it is. These are building boards. This is just airspace. By itself, air is an insulator, but not a very good insulator, you see. It's a 1.0. But then you got real good insulators, that are made particularly for insulation. R19 mineral fiber with 2.6 wood studs, 19, you see, very high. 19. And then this is 8, 7, so the bigger you're getting, the better the insulating material it is. Then you got masonry on concrete. So those are not very good insulators. A 4-inch brick, it's very, very thick, it's only 0.8, you see. And 0.8 literally means it takes 0.8 Fahrenheit difference to cause 1 temperature, 1 BTU to transfer. You see, 0.8 is not that much, you see. Flooring, hardwood, tile. Tile is not a good insulator at all, you see, 0.05. Carpet is good insulator, 2.08. Carpet with rubber pad. roofing, asphalt shingles, wood shingles, 0.97. Glazing, double pane, single pane. You see, oh yeah, that's very important, the windows, right? Single pane is 0.91, double pane with a 1/4 inch airspace. So right, double pane windows are like basically 2 layers, and then inside of it is an air layer, right? So 1.69. You see, so you're by going from a single pane to a double pane with a 1/4 inch airspace, you're increasing the R value by 2 almost. So that you're decreasing your heat loss through the windows by 2. That's a lot. From single to double. You know, so imagine all the heat you lose through single pane. And then you have to put in heat, electricity, you're spending money, so it's definitely worth it. Then you go to 1/2 inch space, 2, 3/4, 2.38. You see, so you can kind of make a cost analysis, say, bring somebody over, say, what if I put a 3/4 inch? It's probably gonna cost you more, but is it gonna be worth it? Are you gonna save enough to do a cost analysis, you know? Definitely from here to here, it's worth it. But then I'm not sure if it's worth it. Probably it is, you know, depends on the cost. Triple pane with 1/4 inch, 2.56. Triple pane with a 1/2 inch, 3. Wow, I didn't even know there's a triple pane. So 3 layers. Doors, wood solid core, solid insulated metal door. So you see even that, you're losing heat through the door, yeah.
What does that look like, that layers of like paint? Can you like maybe illustrate it a little bit?
Oh, you wanna see maybe an image? Yeah, I see that. Pretty nice. So it would look kind of like this. You can kind of oh, this is a single pane. See here, the double pane? So with the air layer. Like that. Pretty good. Let's see what the triple pane looks like. It's pretty good. Wow. Boom, boom. And then you're adding air. Air is a heat conductor, but its insulation is better than the glass. So you are definitely saving money. R values in the triple pane was 3 compared to the single pane 0.91. It probably also depends on how many windows your house has. If you have 1 window, let's just say, well then probably you're not losing that much heat. But if you have a bunch of windows, then it's worth changing probably, because you're gonna lose a lot of heat through there. Okay, so you can kind of get the idea of the R value. Okay, so now we know that the R value simply adds up in series, just additive, right? So whereas the conductivity, opposite happens. The 1 over the conductivity adds up. So now how about the parallel? Okay. So parallel would be something like this. Let's say you have a wall, and then let's say part of the wall is your window. Of course, in most cases, the window will be thinner than the wall itself. It would be something like this in reality. Let's say here's the window. Kind of like you see here. You see, so this is parallel with this, because the heat can come in either through there or through the wall. You see, they're not in series with each other. When it goes through here, it doesn't have to also go through the wall. You see, so this is in parallel, but of course, this is not the same thickness as that. But let's just make it for now, let's just make it the same thickness. So that means if this is T1, T2, T1, T2, so the heat can go through there. So we'll call that P1, K1, and then or we can call this here P2, right, and this is K2. So the heat can either go through there or through here. The other kind of way we can visualize in parallel is something like this. Let's say something like a cup of coffee, right? The heat can either go through the side wall or here, right? So this, the side of the cup is in parallel with the bottom, even though it doesn't look like that. And then if I had another kind of material at the top, right? So you would have three things in parallel with each other. The top, the side, and then the bottom. You see, those would also be parallel. If the top is open, then you lose heat through radiation through the top, not conduction, right? So then it'd be radiation, and then conduction and bottom conduction are parallel, you see. So then, in that case, what is the same and what adds up? So this changes, right? What adds up is the power. The total power that's coming in, P total, is the sum of P1 plus P2, right? So a certain power is coming through there, plus a certain power of heat is coming through there, and the powers add up. So it's P1 plus P2 equals P total, you see? So it's kind of like resistors in parallel. How would they add up? So resistors in parallel, what adds up? It's the current, right? I total. So a certain electrical current comes and then splits into two, and then the total current is equal to the sum of the currents, right? But what is the same? It's the voltage drop across this resistor, the voltage drop across this resistor, they're the same. And they're equal to the voltage of the battery. So then how do the resistors add up? Then you use the equation that connects voltage and resistance, and then you say, oh, which one adds up? So you look at the one that adds up, you solve for that variable, I is V over R, then you substitute, okay, therefore I total is equal to V total over R total, and that's equal to V1 over R1 plus V2 over R2. So that's always what you're doing is, what adds up, what is the same, then look at the equation, look at the one that adds up, solve for it, then substitute, and then get rid of whatever is the same. So then V1, V2, V total. So then 1 over R total is 1 over R1 plus 1 over R2. So that electrical resistors, when you place them in parallel, they reduce each other, right? So if you take a 20 ohm resistor and a 10 ohm resistor, right, and you put them in parallel, the net resistance should be less than even the 10, right? So it's gonna be 1 over R total, 1 over the 10 plus 1 over the 20, right? So then you can get a common denominator, 2 over 20 plus 1 over 20 is 3 over 20, and then reciprocate it again. R total is 20 over 3 6.67 ohms. Right? So then, if you have a 20 ohm resistor and a 10 ohm resistor, the net resistance in parallel is 6.67 ohms. And the logic behind it is because by giving two resistors in parallel, you have allowed the current two choices to go through. And so it's easier for current to flow through that circuit. You're able to squeeze more current out of that battery, more juice out of that battery, because you said, oh, you have two pathways to take. So you've made the resistance of the circuit less, you see? Well, two heat conductors in parallel, same thing should happen, you see? By allowing the heat to escape through the top and the sides and the bottom, the net heat resistance of the circuit should be less than either the top, the sides, or the bottom. By allowing the choice of heat, oh, whichever way that I want, I can escape. Oh, okay, then that's good. But if I insulated the bottom so well that I cut it out, heat can't escape, then the resistance is more now. You get the idea? So by adding resistors in parallel, I should be decreasing the resistance in heat. And same idea, by adding more pathways for the current to take, I should also reduce the resistance. Okay? So the same idea should happen. You see, whereas in series, when I add the resistors in series, heat resistors, I'm making it harder for it to go, because it's got to go through all the heat resistors. See? So then the next thing to do is to say, okay, what adds up? What is the same? Okay, we never said that. So what is the same in this case? Right? We said the power adds up, but what is the same? It should be similar concept as to here. What is the same? Voltage, right? And the equivalent of voltage for heat is temperature difference, because there's temperature difference that drives heat flow, right? So temperature difference is like voltage. So that means temperature difference is the same. And you can kind of see why. If the window is open to the outside and the wall is open to the outside and they're both open to the inside, then the difference between temperature here and here and here and here are going to be the same, you see. So then you're going to have, so the temperature difference is the same. So now look at the one that adds up and then use the equation that connects that to the rest, right? So which is what? Our famous equation, Ka delta X over H. So I'll replace delta X by H. So then you're going to have here, P1 is going to be K1A1 over H1 delta T1 plus K2A2 over H2 delta T2 is equal to K total A total over H total delta T total. And then whatever is the same, you cancel that. And then what else is the same? H1 is the same as H2. It doesn't have to be, like I said, in the case of the window, it doesn't have to be. But let's just say, for example, that the H1 and the H2 are the same thickness. If they were, then H1 would, if they were the same thickness, then H1 would cancel. Then you would get K1A1 plus K2A2 is K total A total. So what would A1 be? The surface area of this, the surface area coming this way. And then the A total would be, A2 will be the surface area of this guy, of that one, and then K1, A1, K2, A2, and then A total would be the sum of the two surface areas, right? So the conductivity, the way that they added in series was the other way, right? It was H1 over K1 plus H2 over K2 is H total over K total. And then I substituted, this became R1, and this became R total. So this one ended up being K1A1 plus K2A2 plus equals K total A total. Now, if I want to write that in terms of the insulation factor, in terms of the R, H over K, what I would do is not assume that they're the same thickness, which is even better because sometimes they aren't the same thickness. So bring back the H1. Well, you know what, even this equation, I could write it with the H1. I don't have to assume that H1, H2, H total is the same. I could just write it like that because, like I said, the window can be a different thickness than the wall, right? So you could just write it like that as a general equation. Then what you would do if you want to write it in terms of R, this K would come down to the bottom here, and you'll write A1 over H1 over K1, right? And then H1 over K1 would be the insulation factor. So then it'd be A1 over R1 plus A2 over R2 is A total over R total. So this came down to the bottom. This came down to the bottom. And then this one came down to the bottom. Now it kind of resembles the way resistors add up in parallel. Electrical resistors add up in parallel. But not quite, because it's got surface area that we have to worry about. In series, it looks exactly like the way electrical resistors add up in series. But in terms of parallel, it looks a bit different. A1 over R1, A2 over R2, and A total over R total. So let's just give an example. Let's say something like this. You have a cup. So let's say the thickness here, 0.2 centimeters. Let's say the thickness here, 0.3 centimeters. And let's say you close the lid so that you have now all four sides. So then, now let's say this is 0.1 centimeter. So then let's say this material, let's give the R value. So let's say, what were some R values? Okay, so like glass is 0.14, just to give you an idea, 0.14 right here. Okay, so I just kind of wanted to use a realistic R value. So glass is 0.14, and anything like, of course, we know glass is not a good insulator, so anything like 1, 2, 3 is a better insulator. So we can make this one, let's say 1.2, and then that would be, the units would be of Fahrenheit. Feet squared, was it Fahrenheit feet squared, hour over BTU. In other words, how much Fahrenheit difference does it take for 1 BTU to go through 1 foot squared per every hour, right? And then this one, let's say, is R value of 1.8, and then let's say the top is a better insulator. R value is 3.0. So first thing we can say is, what's the total R value of that mug? What is R total of the mug? And then B, here, let's say, let's say the outside is 25 Celsius. So you have water here up to 60% of the height. Make the water blue. And we'll give this some dimensions. The radius is 4 centimeters, and the height is 8 centimeters or 10 centimeters. Okay, I think that's all the information we need. So we'll ask a R value question, and then how long does it take for something to happen type question. Okay. Okay, so then in this case you don't have any heat insulators in series. They're all in parallel, right? So the side is one heat insulator, the top is another one, and then the bottom is another one. So you have literally 3 heat insulators that are in parallel. So it's gonna be A1 over R1 plus A2 over R2 plus A3 over R3 is A total over R total. So A1, so let's say this one, the bottom one I called R1. So the A1 is gonna be the surface area of the bottom, right? So pi times the radius of the bottom, 4 centimeters, right? 4 centimeters squared, that's the area of the bottom, divided by R of the bottom, which is this one. I have to do something with the thickness. There's something with the thickness that we gotta do. So, and then plus the surface area of the side, which is gonna be what? 2 pi r times the height, right? 2 pi radius times the height over the r of the side, which was 1.8, is equal to, oh no, plus the surface area of the top, right? Pi times 4 centimeters squared, so this is also centimeters squared, over 3.0, that's equal to A total, which is the sum of the surface areas, right? So pi times 4 squared plus 2 times 4 times 10, so let's write it here. Pi times 4 squared plus 2 times 4 times 10 plus 4 squared over R total. But if we do this, we're making one mistake because we haven't included their thicknesses, right? The respective thicknesses. In this table that we saw, how are the R values given? R values for various materials normalized to a 1-inch thickness. In practice, the values will have been obtained using different methods and thicknesses. Typical values are approximations based on the average of available figures. The last column gives RSI values normalized to a meter thickness. So, in other words, these ones are per inch of the material. And these are per meter of the material. So in other words, because R value depends on the bigger it is, the bigger the R value, right? So they're normalized to some thickness. So the inch ones were normalized to 1 inch. So in other words, what this means is the R value of this is 1.2 if it's 1 inch thick. You see? If it's not 1 inch thick, then you gotta multiply it by the thickness, whatever the thickness it is. So in other words, how would I find the actual if this is, so basically it should be written like this: Fahrenheit, feet squared, hour, BTU per 1 inch of the material, right? So then if I know that the thickness is not 1 inch, I have to say multiply it by 0.3 centimeters, and then you can say 2.54 centimeters is 1 inch. Okay, so the actual R value, since these are per normalized to 1 inch, then I multiply it by the actual thickness. Then I say 2.54 centimeters, and so this is just simply a conversion. So then what happens? Centimeters cancel centimeter, inch cancels the inch. So the true R value of that material is simply the value given times the thickness, which is 0.3, okay? So then when I come to this, I should simply do times 0.3 times the thickness of 1.8, which is gonna be 0.2, and then times thickness of the 3.0, 0.1, and then is equal to this over R total, and then the R total that I get is the total R total. I don't need to put anything times the thickness.
Wouldn't it be 0.3 over 2.54?
Well, because if they're all 2.54, let me see.
Because it's how you're doing it before, right? They all cancel.
Oh yeah, hold on. If this is 2.54, but if I don't put the 2.54 here,
Because before you were canceling if it's like delta T1.
yeah, I
plus
see, you
delta
know what?
T2
If I
equals to delta T total.
forget to include the 2.54 down here, 1 over 2.54, 1 over 2.54. So well, I could either also put it here. Okay, yeah, you know what? If I put it here,
It all cancels out.
then it will all cancel out, and the units of our total will come out what? This is a unit thing. Let's see, the units of our total will come centimeter squared will cancel. This one is 1 inch, centimeter.
Yeah. It should be the same thing.
Centimeter?
Per 1 inch of the material.
Still the same thing.
Times 0.3 centimeters, 1 inch.
And then just like a common denominator.
Yeah, I'm thinking if I want the total, if I want to know the total R total, in units of Fahrenheit feet squared hours per BTU, do I include the 2.54 here or not?
Well, you can see it as it's multiplying the numerator instead of the denominator because it's a fraction.
Yeah, but if I include it, then all the 2.54 will cancel, then I don't need the 2.54. But if I don't include it here, then this will go up to the top, and then that will change the answer that I get here. You know, so let's see if I include.
It should be included to our total because it's affecting the R initials that summed up together.
Per 1 inch times. So this is per 1 inch. Okay, look, if I include it there, this one cancels, the inch cancels, the centimeter cancel, and the units is that. So if I want the R total of this material, not per 1 inch of the material, but the total R total, I should not include it here. Yeah, I shouldn't include it. In other words, I should only include it on the left side, right? Because I want to know what the total R total of the mug is, not per 1 inch of thickness. I want to know the actual R total of the mug for its thickness, the different thicknesses that the mug has. So I shouldn't include here the conversion, right? So then it will only be on the left side, which means it will go up to the top, go up to the top, go up to the top. And then calculate all of that. So now the pi's will cancel, of course. Pi, all cancels out. So I just need to do, okay, so 4 squared, which is gonna be 16 divided by, what was that?
And what did you call that again? The for 1 inch
Per 1 inch of the material.
per 1 inch of the material.
Yeah, so 16 over 1.2 times 0.3. 1.2 times 0.3 is that 3.6. 1.2 times 0.36. Right? Plus Oh, no, I should include the 2.54, because the 2.54 goes up to the top, right? Let's cancel, so 16 times 2.54 divided by 0.36
So
plus, the second one is gonna be, 8 times 10, 80, right? 80 divided by 0.36, or also 0.36, huh?
So then you say that, you must account for the R per 1 inch of material?
Yeah. Yep. So 80 divided by 0.36 again? Oh, no, times 2.54 divided by 0.36 plus 16 over, and then this is gonna be 16 times 2.54 over 0.3. Plus 16 times 2.54 divided by 0.3. So I'm getting 812. This whole thing comes out 812.8 is equal to this guy, 812.8. So when I include the 2.54, it comes out like that. And then that's gonna equal this one, 16 plus 80 plus 16 over our total. So then that's gonna equal 3,212 over our total. And then our total is gonna be 112 over 812. So, power -1 times 112, 0.1377. 0.13779. And the units of that will just be Fahrenheit, feet squared, times hour over BTU. Not per 1 inch of the material, right? It's not per 1 inch. It's per, that's it. It's just, that is the unit. In other words, we got rid of the normalized per 1 inch factor, and we said that's the total R total. Remember that we said earlier, the R of the glass is not a very good insulator. Remember I said the table was 0.14. But that one was in units of Fahrenheit, feet squared, hour per BTU, per 1 inch of glass. Okay, but of course our thicknesses are less than 1 inch, right? A lot less. So it kind of makes sense that our total is about 0.14, but even with thinner. In other words, if our material of the mug was much thicker, what would our R have been? Much bigger than glass, right? So our mug would have been a better insulator than glass, in other words. So that's why this shows you that this is the total R total, including the thickness of the mug. That's already included. You get the idea? It's kind of confusing, huh? So the 0.14 is including 1 inch of glass. So if you had a mug made of pure glass with the same thicknesses that we had, our total would have been a lot less than 0.14. You see, it would have been like 0.0 something. So that is the answer, yeah? That answers what is the R total of the mug, right there. Okay, now if the mug is full of water at 100, so go back to the Newton's law of cooling. What was that?
And so had the mug been, the thickness been 1 inch?
Yeah, if the mug had been 1
1 inch
inch
over.
thickness, 1 inch thickness, 1 inch thickness, 1 inch thickness, our total would have been a lot more than glass. Lot more than this. Yep. Okay, so now Newton's law of cooling. Ln delta T is equal to Ln delta T initial minus, what was it? MC over DAC, I think? T. No, DA.
Oh, it's K,
K
K,
over,
K over,
DMC. So that means the bigger the conductors, bigger the area, the less time it takes to cool. Yeah, the bigger the conductivity, the bigger the surface area, less time. The thicker it is, the more mass it is, the more specific heat it has, the bigger the time. Yep, that makes sense. Right, so we can straight go to Newton's law of cooling and then put Ln delta T. So we want the temperature to go to what? 70 Celsius, right? And then the outside is 25. So that means we want the final delta T to be what? 70 minus 25, right? So if this is 70, and then the outside is 25, so that's gonna be 45, right? So we put here 45. The initial delta T is what? It starts out as 100. 100 minus 25 is 75. Minus, okay, so now where does the R factor go in? The R factor that we got. Notice K over D. So what's the definition of R? H over K. So basically the K over D is the reciprocal of the R factor, the net R factor of the mug. You can see the K over D. So we can replace K over D by R in the bottom. You can see? And that's the net R factor of the thing. So we can just say A over K can come down to the bottom and make this a RMC. And the K over the D is the net R factor that we got, this guy. Okay, so we have here, we could bring this to the right side, left side, bring that over there. So we have A over RMC, T, ln of 75 over 75 minus ln of 45. Okay, then area A is the total area of the mug, which is the same thing that we had before, the pi times the, I could do it in centimeters, 4 squared plus 2 times 4 times 10 plus 4 squared centimeters squared over, and then T is T, specific heat of water I'm gonna use. Oh, hold on. Remember, we're told that the water is only full up to the 60% of water. So the surface area of the water, hold on.
6 centimeters.
Oh, you know what? Let's just make it totally full, because then, oh, then it makes it a hard problem if I do this, because then they're losing heat this way. It's like having 2 conductors in series. It's got to go through the air, it's got to go through the top, so we have to now do 2 resistors in series, right? So you'll have 2 resistors in series and then 3 resistors in parallel. Oh, makes it hard. Forget it. Let's just make it completely full of water.
Already past 101.
So,
That road.
but you get the idea, right? So if it wasn't completely full of water and there is a mug, so then we just have to say, okay, it's got to pass through a layer of air, then the top. So now we have to do the conductivity of air, conductivity of the top lid, and then all of that. So let's just say it's touching it here. Okay, so then that's fine. So the area we can include. So we'll just say up to the top, up to the top. Okay, so then what's left? The mass, the specific heat, we can do 1 calorie. The specific heat of water, 1 calorie per gram Celsius, right? And then M is the mass of the water, which is its density times volume, right? So the density of water is 1 gram per cubic centimeter. And then what's the volume of the, so pi r squared times h, pi times 4 squared times 10, and then the pi cancels. So this is centimeter cubed. So notice how the units are working out. Centimeter cubed is canceling. Gram is canceling. Okay, now the R value. So now we get to practice again how to change. Remember, we practiced how to change from calories to BTU to all of that. So 0.13779 Fahrenheit, feet squared, hour over BTU. So then we say 1 BTU is 1055 joules. 4.184 joule is 1 calorie. So I'm converting to units of calories per centimeter. Okay, then I'm gonna say 1 Fahrenheit is 1.8 Celsius. Or is it the other way around? Is it 1.8 Fahrenheit is 1 Celsius? Sometimes I get those inverted. So remember, it comes from this equation. You take the derivative of this, you get.
The Fahrenheit increases faster than Celsius, right?
Yeah, so 1 degree unit of Celsius, DC1, is 1.8 Fahrenheit. So opposite. So then it says 1 Celsius is 1.8 Fahrenheit. It's the other way, right? So 1 degree Celsius is worth more than Fahrenheit, you see? So then the Fahrenheit cancels the Fahrenheit. BTU we already got rid of. So then the feet, 1 foot is 12 inches. Or you know what, I could go directly to, yeah, I could say 3.281 feet is 1 meter. Square that. 1 meter is 100 centimeter. Square that. So then the meter squared cancel the meter squared, the foot squared cancel the foot squared. Then you're gonna have what? What's left? Oh, the hour, 1 hour is 3,600 seconds. So then, whatever number we get here, we're gonna get some value of R, right? What are the units of that gonna be? It's gonna be Celsius, centimeter squared, second, right? Celsius, centimeter squared, second, over calories. right? And then look at what's gonna happen. Celsius is gonna cancel Celsius. Calories is gonna cancel calories. Centimeter squared is gonna cancel the top centimeter squared. And then seconds is gonna cancel our answer for T, right? Which is seconds. Then on the other side, you're gonna have ln of ratio of 75 over 45. Okay, so what's that number come out? Just this number here. You guys do that, tell me.
Uh, 985 point.
985.7809.
7809.
Okay, so then put that into here. Then you remember you have 4 squared times 10.
4 squared times 10. That's it. Okay. 7, 7. I have 7.1 10 to the negative 4.
Yeah? It doesn't sound right. 7.1 times 10 to the negative 4 seconds? Because the number we
wait,
get
no.
should be realistic.
I didn't put that. I only did one side.
Oh, you didn't put the ln?
No, not yet.
And then how about the top?
Oh yeah,
And that's a 1,055, so it's under BT.
1055.
Yeah.
so and then now 75 over 45 over okay, just go. Oh, 790.37.
719.37 seconds, which is how many minutes?
60, right?
30.
11.99.
Yeah, so I'm expecting an answer that's not too long, because if you have a hot water at 100, the initial, it shouldn't take too long to drop to 70. The initial 30 degrees should happen pretty quick. After that, from 70 to 40, the next 30 degrees should take longer, right? So from 70 to 40, it should take longer. From 40 to 25, it should take the longest. So 11 minutes, yeah, that makes sense, 12 minutes. In other words, if I wanted to say, how long does it take to go from 70 to 40? How would we do that? Well, then this would change to what? 45 over what? 15.
Oh,
You see? From 70 to 40. So if you say, okay, increments of 30 Celsius, and you should notice that the next 30 Celsius should take a lot longer. The next 30 should take a lot longer, you see? Because now the ln of 45 to 15 is what? ln of 3, right? Versus being ln of smaller number. So now that should probably take 20 minutes, 25 minutes.
25.79.
So I just guessed 25 minutes, you see that? Because everything else is the same, the area, the R value is the same. The next from 70 to 40, it should take 25 minutes. So in total, it takes 36 minutes to drop to 40 Celsius, you see? But the first 30, it takes 12 minutes. Then after that, 25 minutes. Well, there's no next 30 because the temperature of the outside is 25, so you just let 15. But remember, you never can reach 25 because if you do, what happens? You get a 0 here. If you ever reach 25, you know? So you get, let's say you go from 70 to 25. So you have left with ln of 45 over 0, which is undefined. That's why you can never reach the temperature of the outside. You're getting a different answer?
Oh.
Yeah, I got
1015.
yeah.
101. Oh, a little bit bigger.
What did I do?
This one was 0.13779.
1.13779 times 4.184.
4.184.
100 squared times 3600.
100 divided by 1055
times 1.8 times 3.281 squared.
squared. 1,000?
Yeah, I got 1,015.
Oh, okay, slightly bigger.
Update your calculator.
Yeah, come on, we can't always trust Lane, you know. She's trying to throw the rest of the.
You know what?
She's trying to throw the rest of the class
I
off,
plus
you know.
101 with this, so
Yeah.
I don't care. I don't need help.
1,015. Okay, which means the time is a little bit longer than what we got. It's not gonna affect it that much.
Me too.
As long as you're in the ballpark on the test, you know. But of course, no. On the test, I'll look for those errors, right? Okay, I think that kind of ends chapter 17. And then the shorter chapter, chapter 18. Let's do